All right, 10:30. Let's get going. So, second weekly meeting of Aerospace Engineering, AE 112. I guess it's not Aerospace Engineering AE 112, SJSU AE 112. Brought to you by the COVID pandemic, so we here online. Today we're going to be going through distributed forces, centroids, and review problems. That's not true. I should have redone these slides. We're going to do a centroid problem, and we're going to do a homework problem. So if you're not aware, I had a community point thing, where you could add your Twitch points into a pile of basket with other students. And if I hit 10,000, which I hit in like 4 minutes, just dumb, I would pick a homework problem and I would do it. So I'm going to do that again, probably like every 2 weeks, but I'm going to increase the point value tremendously so that it does not take 5 minutes, that it might take a day or something. I don't know. So that's what we're going to do today, a centroid problem and a homework problem. So let's start out with watching a video. Homework problem 2 hurts my head. I got something for you today. Okay, so let's go here. Nope, here. Sorry, I just came because I'm going to recap me. You haven't missed anything, Ryan. You're good. We're going to watch a video right now.
I'm ready.
Are you ready, Albert? What's the tips number?
Looks shiny.
We've started this whole project back in February of 2019, so about a year and a half ago. The Flying V is a new aircraft configuration. The fuselage and the wing are integrated in one body, and that means that the airplane consumes less fuel than a conventional tube and wing aircraft. The scaled model has been designed not only to demonstrate that the Flying V can indeed fly, but also that we can actually do tests with it. We can make maneuvers with the airplane and then measure the response of the airplane. So in that sense, it's really a scientific vehicle that we use to perform tests with.
We do plan to have hopefully a few flights today, so that we can at least get some useful data that we can go back and analyze and also plan further flight tests.
Yeah, it's getting a little tenser towards that moment of first flight, absolutely. And I know the whole team is feeling that.
It's sunny and there's a light breeze, so it looks like it's the perfect conditions actually for the flight. We've done all of the checks that we need to do. I'm confident in the pilot, and he's calm. And if he's calm, then I'm calm.
There's one particular feature of this plane that's very unconventional. If we are exceeding a certain angle of attack, then there's a sudden nose-up pitching moment. So it's becoming unstable.
Yes, give some throttle. Yeah.
Right side, yes. Yes, left side also. I'm ready.
Are you ready, Albert? Yes, we are ready. Five, 7, 9, 11, 13, 15, 20, 22.
In the air. I continue.
Yes, babe. 24, 25, 28. 33. Batteries are at 80. And you're currently at 6 degrees. It's a bit heavy. Moving back, clear. Speed is good. Speed is high and good. It's been 2 years of intense, stressful work to reach this moment, and then to have it confirmed that it flies, all of that hard work. It was worth putting in all of the hours, making sure everything's correct and built properly, built accurately, and it pays off. I think we're all happy that we succeeded and achieved the goal of flying the flying V.
That that music choice, right? So, thank you to Maki Clark for submitting that video. Again, if you guys want to submit a video, then go ahead and go to modules, cool videos, submit something there, watch them or check them out, and then decide what to incorporate into class. I had one submitted that was like 59 minutes long, kind of a mini documentary. So if anyone wants to have an 8112 movie night, where we, get together some night of the week and we check out a longer video, let me know, because it was a good suggestion. So if you want to do that, speak up. Hans Zimmer. Don't attack Hans like that. You guys are funny. Okay. Let's get going. Oh, announcements. So, Ryan, you didn't miss anything. So I put the announcements after the video because, let you guys filter in. So Quiz 3 Alpha goes live after class today. There'll be 3 problems. 2 of them are super easy. Kind of give me points. And the second one is where we're really going to be testing your problem-solving abilities. So free body diagrams is you're going to have pins or hinges or rollers or a bunch of different types of objects that are available, and you have to put in the reactionary forces and the unknowns and report in an integer form how many unknowns are there. So on your paper, your submission, you'll write the free body diagram, count all of your unknowns, submit that as an answer, and those first 2 questions should be easy clap. Second question is a concentrated load on a beam. Pretty simple. But you're going to need to use moments in order to solve it, because that's what we've been doing, right? Using moments. No more f of x, f of y, f of z to solve these problems. You're going to need to use moments to determine them. And that'll be it. Any questions on the quiz? Pretty straightforward this time. Oh, and I knocked it down to 60 minutes because I would really like you guys to be able to finish this in like 25 minutes. This should not take you the entire 60 minutes. I want to lighten the load of my quizzes on everyone. Okay. Learning outcomes for today. We're going to compute the centroid using standard geometric shapes. This is a review slide from Tuesday, where we decided the weight of the object is, or the weight of the distributed load is equal to its area. Just reviewing why we're doing this. So the distributed load can be replaced with a concentrated load of a magnitude equal to the area under the load curve. Something that we're not going to deal with today. What we're going to deal with, the line of action passing through the centroid of the load area. We had very geometric shapes that were pretty easy to add up. I'm going to go through a slightly more complex example today, and we're going to introduce a new organizational method for keeping track of the calculations and what you're going to be doing to solve these. Hopefully be a little more clear. Nothing new on this slide. Let's go through the example. Okay, so go ahead and get started with this problem however you like, and I'll jump back with you as soon as I get my pictures drawn. Okay, so I have just redrawn the picture, and now we're going to talk about what I'm actually going to be doing to solve this problem. My circle looks really small. Okay, so like textbook for a bad picture here. So when I think about how to find the centroid, it's easy when I can just add simple shapes together, but this time we're going to think about subtracting simple shapes in order to get a more complex shape like this. So first off, I'm going to start by drawing the bodies again. And I'm going to call one C1 and the other one C2. Okay, and if this was the entire shape, and I computed the centroid, it would be a little bit off because there'd be extra mass in this corner or in the side where the half sphere is, or the half circle is not. So I'm going to take this and I'm going to subtract this. And so that will equal C. We happy with that reasoning? All right. So the way we're going to do this, keep track of things, is by making a table. And in the beginning, with problems like this, we can go ahead and do the table by hand. Later on, I'm going to give you guys, well, I'm going to start making an Excel spreadsheet that makes this calculation not easier, but a little easier to keep track of and less prone to errors. Okay, so let's make the table. Parallel lines are hard. Okay, so we're going to put C1 here, C2, and the summation of them. I'm going to put area up here. We're going to do X bar. Y bar. X bar times the area. Y bar times the area. Okay. And so we begin the calculations of C1. So C1 is 30 times 50. Unmaking my bed again. Dang dog. $30 times 50, 1,500 inches squared. Okay, area of C2 gonna be pi r squared, and we're gonna divide that by 2 since we only have half of it. So pi times r is 15. Divide that by 2. 353 inches squared. Okay, now we can move on to the X bar, and we're going to be using X bar of commonly known shapes. And for the rectangle, it's going to be right smack dab in the center. So in the X direction, I've located X horizontally to the right. So H1, H16, B22, we might be able to. Somebody else is probably better at that than I would, though. Okay, so X bar is going to be halfway through, so we're talking about 15 inches by inspection. The X value, well, let's do the Y value first. Again, halfway up, so if it's 50, we're looking at 25 here. And if we move over to the C2 in the X direction, anybody know the centroid centroid calculation for a half sphere or half circle? Probably don't, I had to look it up. Hog. I don't remember it, but I know I was taught it. Yeah, I was told that it first comes into play in physics as center of gravity. But it is going to be 4r over 3 pi. Is that right? Yeah. 4 over 3 pi. 4 times 15 divided by 3 times pi. That's not right. It's the opposite way around. I ruined that. 4 pi over 3r. And I know that because 62, it's only 15 inches wide, so it doesn't make any sense. So 4 pi over 3r. 4 times pi divided by 3 times 15. Why did I ruin that? Did I do the same calculation? Divided by 3 times 15. What? What am I doing here? Four times pi.
There's a chart on page 193 of the textbook, and it says the centroid, the y component, is 4r over 3 pi.
Didn't I do that first?
Yeah.
60 divided by 3. I must have messed this up here. 60 divided by 3 times pi. Divided by 3 times pi. There we go. Makes sense. But why didn't that come out properly the first time? Dang, I had to double back. Four times r. Was that Javane? Who jumped in there and helped me out with the page number?
Oh, that was me, Stephanie.
Oh, Stephanie. Yeah, put that in the chat. Oh, you did put it in there. Page 193. Thank you. Okay. 4r over 3 pi should equal 6.3. But that is 6.3 from the right side going to the left. So it is somewhere here. 6.36. So in order for me to report the y bar location, I'm going to have to take the entire 30 and subtract 6.36. Why did I do that? 30 minus answer equals 23.63. Okay. That's the wrong box. What am I doing? The y bar location is going to be at the center of the radius, or center of the circle in the y direction, which this location is going to be 30. Busting out the big guns for this one. Okay. Now we're going to carry out some calculations, and this is where, if you're not doing it with Excel, we can make some mistakes. We're going to multiply x bar times 1500 inches and put that answer here. $22,500. And the units on this are going to be inches squared plus inches times inches, which will make this inches cubed. And then 23.63 times 353, 8,341. I'm not going to write inches cubed. And same thing with the y components. 25 times 1,500, 37,500, and 353 times 30, 10,590. Okay. Now, time to sum these, and automatically the only two columns we don't sum are going to be in the x bar and the y bar. Those ones are going to be summed when we multiply the area here. So we can sum the area. And the thing about summing the area is that this 353 also makes these negatives, because I am subtracting the area of C2. So this is actually negative area, which carrying in the calculations makes this negative area and makes this negative. So 1,500 is a total C1, and I'm going to subtract 353, and we're going to come out with 1147 inches squared. Total area of C1 minus C2. Oh, this kind of looks like an 80. But based on the picture, 30 times 50. Okay. And now we'll add 22,500 to negative 8341. 1114,159. 37,500 minus 10,590. 26,910. Okay. And now we are ready to find X bar. I'm going to go back up to my known, and these are lowercase x bars, which means they're intermediate steps. The entire x bar of the system I'm going to denote with a capital X and a capital Y. And these should be reported in inches. And to add them to my drawing, I'm going to put an arbitrary place here and call this Y bar. And I'll put X bar in here somewhere. Okay. And so to find X bar, and Y bar, and seems to be running out of ink. And so X bar is going to equal the summation of X bar times A over the summation of area. And so X bar A, 22,500 over, oh wait, summation. Ruin that one too. This is why you do the Excel spreadsheet, so you don't make simple mistakes like this. Because it says the summation of XA, which is the summations down here. 14159 over the summation of area. 1147. 14159 divided by 1147. 12.3. That makes sense? X bar. So if this was a standard rectangle C1, X bar would be at 15. Since there's a hole missing, the centroid move over to the left, so this answer makes sense. 12.3 inches. We'll do the same for Y bar. And that will be 26,910 over 1147. And remember, these are inches cubed, and these are inches squared. 26,910 divided by 1147. 23.5. Okay, sanity check. If this were right in the center, it'd be 25. But since there's something missing, it's going to push it down to the left, or push it downward. So less than 25 makes sense. Okay. Any questions on this one? Shu Tatsuyu, you get 62.8 when it's 4r divided by 3 times pi. Yeah. That's not, that can't be right. So if you actually do 4r divided by 3 pi, like this, it will work out. Okay. We box the answers. Move the camera to take a picture. Okay, and we go back to the lecture. So we're going to be going through some more centroid problems. This one's just a nice, easy one you could do by hand, but it introduces the basic concept of adding and subtracting standard geometric shapes in order to get more complex geometric shapes. Okay. Take a break. We're going to go through the homework problem, and it's going to take a long time, so stretch, grab some water. It's 11:02 now, and I will be back at 11:07. This was a link posted in the Twitch chat for those of you not in there. And the accommodating question is, hey sir, can you help me explain the math behind this article? I don't know. This is a good one here. Air traffic control directs you to climb from 20 to 29,000 feet and to be level within the next 6 minutes. That you need to maintain a minimum climb rate of 1,500 feet per minute squared. $9,000 feet in 6 minutes. But you need to be straight and level, which means the climb like the transition to climb and the transition to straight and level need to also happen in there in 6 minutes. So 9K divided by 6. Yeah. 9K divided by 6. Fuel burn awareness. This is where they got the 1500 feet per minute squared. Burning 2400 pph. Pounds per hour? I don't know what pph stands for. Anybody know what pph stands for when you're burning fuel? Yeah, that makes sense. Look, you have 5,000 pounds of fuel on board. 5,000 pounds of fuel? How many gallons is that? Pounds per hour, yeah. But how many pounds is 5,000 pounds of fuel? If you use water, water's 8.8 pounds the world round, is that right? 5,000 divided by 8.8. 568 gallons of fuel? Oh.
Joseph, it's 6.7 pounds per gallon of Jet A.
Okay. 5,000 divided by, what did you say, 5.6?
6.7 pounds per gallon, per US gallon.
750 gallons of fuel on board?
That's nothing in a jet.
I understand that they're burning, they can only fly for about 2 hours. That's what this article's telling me. But still, 750 gallons of fuel. Dang. Okay, we're back now. This is a good tangent. Thank you so much for putting that in the chat. Let's get on to the homework problem. Okay, so we start this problem like we do any other problem. Free body diagrams. Ready to go. I'm going to start mine up real quick, and then we'll be back with you. That's why they invented flight refueling. Yeah. Okay, so I'm ready to reveal mine. Turn this music back down again. Okay. Then... yes. Okay. So, I redrew the picture. No big deal there. The one thing I did leave off is all the major numbers, because I didn't want to clutter up this particular drawing with that. You can add them if you like, but I'm just going to use a screen for now to keep this drawing nice and clean. And this is my free body diagram of AB. Okay, so a couple things that I did. I changed the crate into the weight of the crate. I changed the boom to weight of gravity, W sub G. Tension, B to H. Tension, D to F. Tension, D to E. Nothing changed there. And since this is a... oh, let's read the... I didn't read the question before we started. Okay. So, a 300 kilogram crate. Okay, right away, first thing I notice is that this is not in forces, this is in mass. Okay, so it hangs from a cable that passes over a pulley. And I noticed that the question in my... so this is pulled directly from my book. In your homework, it does not say over a pulley B. You have to know that this is a pulley by inspection. So I know that it's pulley B, which gives me information about what happens at this 300 kilogram crate over the pulley. Okay, and it is attached to a support at H. Okay, so that's all one cable. From C crate through B and into H, that's one cable. The 100 kilogram, again with kilograms in mass, boom, AB is supported by a ball and socket at A. Okay, so it gave me what type of reactionary forces I'm going to have at A. Ball and socket gives me X, Y, and Z. And by two cables, DE and DF. The CG of the boom is located at G. Determine. Okay. My drawings always look so nice. Yeah, I try to make them look nice. So, that's why at the base, A got AX, AY, and AZ. And despite how they look, they're all positive from this point A. I just use the principle of transmissibility to get AY and move it downward so that I have some space here. AX is in the right spot, and AZ I just backed up from this location to this location. So no trickery going on there. Alright, any questions on the free body diagram? No questions? Okay. So the first thing I always think of when I look at these problems is, okay, what do I know? What have we been learning? How should I apply this? And so right off the bat, I can go back to the question and say, okay, set a 300 kilogram crate. Let's start with those things. And so my knowns are going to be the mass of crate equal 300 kilograms, and the I'm not going to call it mass of the boom, I'm going to call it mass of G to keep the subscripts consistent. That is 100 kilograms. Okay, so in order for me to get newtons, the force, I'm going to have to multiply kilograms by gravity. That's 9.81, but for the purposes of this problem, I'm just going to call it 10. That approximation is fine for this. So for the weight of C, I'm going to call that 3,000 newtons. And for the weight of gravity, I'm going to call that 1,000 newtons. Okay, the problem also told me that weight of C, 3,000 newtons, passes over a pulley B, and so I know TBH right off the bat as being equal to weight of C. Yeah, shouldn't be a big deal as long as the numbers are large enough. 9.81 to 10 is a 2% difference. I just don't want to mess up a number like 300 and then put some other nasty thing here. I just want to keep it simple so we can follow the numbers along and there's nothing confusing about that. You can. On your homework, it should be fine. Just note on there that you use the 10 approximation instead of 9.81. On the quizzes, I wouldn't use that simplification. Because on your quizzes, you only get a 2% plus or minus variance. So if you truncate values like that right off the bat, anything you truncate after that will be even worse. So I would not do that on the quizzes. But on the homework, just note to the grader like I did this. Okay. So, what tools do we have available? What have we been learning? And the low-hanging fruit for me is going to be the position vectors. The problem is full of distances here. So finding the position vectors is going to be one of those comfortable exercises that we've done over and over again. So I'm going to start there. And we'll start with BH. And again, I'm doing BH with the arrow over the top for position vector. Professor Hunter does the R, H relative to B, which means that the letters are swapped with a division sign between them. Notation is hard, but keep it consistent in the classes. Okay, so when I write B to H, I'm going from B to the point H. And so let's go back to the slide. So from B to H in the x-hat direction is going to give me 0.96, 0.84, 1.8, and then 1.5 and 3.9. All those numbers together. So 0.96 plus 0.84 plus 1.8 1.5 plus 3.9. 9 meters. And so from B to H, we are traveling in the positive x-hat direction, so that number will remain positive. And I can move on to the y coordinate system, or the y coordinate. And y coordinate is given to us directly at 6.75 meters. But from B down to H, we're going against the y, the positive y. So that's going to be a negative 6.75 meters. And for the z component, I noticed that C, B, and H are all planar x and y. So there is no lateral movement to give us any z component, and so BH is done. Wouldn't 9.81 be negative? That's a vector thing. That's a vector thing. This is correct for right now, but we'll take into consideration the negative signs a little bit later on. Okay, moving on. Let's go to DH. And DF. Whiteout's getting a workout today. Oh, I wrote DE. Never mind. We'll do DE first. Okay. From D to E in the x-hat direction is going to give us 0.84 plus 1.8 plus 1.5. 4.14 meters. And again, we're traveling down to the right, which means x-hat will be positive. From D to E in the y-hat direction is going to give us 4.95 meters. And we're traveling against the positive y direction, downward, so that will be negative as well. And the z-hat direction is 1.98. And DE is traveling from D to E in the positive z direction. So from E to the x-axis is 1.98 meters. That will remain positive. And let's go to DF. So D is the same place. Oh, they're symmetrical. Okay. So DE and DF are going to be symmetrical about the x-axis, which means I can copy down all these numbers, except for Z will be negative, since it's on the other side of the x-axis. So 4.14 meters in the x-hat direction. Downward 4.95 meters. Y-hat direction. And negative 1.98 into the page, Z-hat direction. Bye-bye. Okay. Position vectors, we happy with those? And normally when we get the position vectors, we go on to do the directional unit vector lambda. So let's go there next. And so TBH vector is going to equal the magnitude of TBH times lambda. And lambda is going to equal, I'll just write it out here, BH over the length of BH. I don't want to put a letter there to denote which one it is, because that's not by definition what it is. Oh, okay, so let's find the lengths since we're going to need those as well. Square root of 9 squared plus 6.75 squared, 11.25 meters. DE 4.14 squared plus 4.95 squared plus 1.98 squared equals 6.74. Is that right? That is right. 6.7 DE 6.74 meters. Since DF is symmetrical, that'll be the same answer. DF 6.74 meters. Okay. Now that we have the lengths calculated, we can move on to populate these. And since I'm going to be going ahead and putting numbers in here, I'm going to substitute TBH right away for this 3,000 newtons. and multiply that by VH. 9 meters x hat plus a negative 6.75 meters y hat all over 11.25 meters. Okay, I'm going to go ahead and carry out that calculation. When I get to r cross f, can you go through put that part a little slowly? Yes. We'll go through that part. Okay, calculation time. 3,000 times 9 divided by 11.25. 2,400. Meters, newtons, so we're in newtons. X hat direction. 3,000 times negative 6.75 divided by 11.25. Negative 1,800. Newtons, y hat. Okay, move on to TDE. And I'm not gonna write this part again. We're just gonna go directly to this portion. So we're gonna do TDE. .14 meters x hat negative 4.95 meters y hat plus 1.98 meters z hat all over 6.74 meters. Okay, I'm going to carry out this calculation and leave the TDEs in. So, 4.14 divided by 6.74 equals TDE 0.614. And I'm going to leave the units off of this because TDE actually has newtons inside of it, like TBH would. So no units on this, it's just a ratio since meters and meters cancel out. X hat negative 4.95 divided by 0.74 equals TDE negative 0.734 y hat. Plus TDE 1.98 divided by 6.74 equals 0.289 yeah. Okay, last but not least, TDF equals. These are going to be exactly the same, so I can skip right over into this equation, and I'm only going to negate the z component. That's the only thing that's going to change here. The 1.98. Make sense? $200 right into your desk. Go ahead.
Nothing. I said yes, it does. I don't have the chat open.
We're talking about something else in the chat. Okay. So, TDF df 0.614 x hat plus t df negative 0.734 y hat plus t df negative 0.289 d hat. Okay, we happy with that? We haven't done anything new yet. These are all tools that we've learned before, that we've applied, that you've been quizzed on. You can all do this part. The next part is where things are going to break down. Don't do this on your paper. I'm doing this just for the purpose of the class to use a paper. For your homework and quizzes, just make a new paper. Bothers me that I don't have anything here. I don't know what letters to put in there to make it apparent. Okay. So, now that we have the directional unit vector multiplied by its magnitude, we can do sum of the moments. Okay, and so if I'm going to apply a tool, let me back up. With these equations, if I wanted to set up a matrix and try to solve these, could I solve them right here? No, I could solve it right here. I'm curious whether or not I could. I'm not going to try right now because I don't want to embarrass myself. But I think that I could set up an equation in the x and an equation in the y. Oh no, I can't because I have ay. Okay, never mind, you can't do that. So because of this, I thought that I had 3 equations, x, y, and z, and only 2 unknowns. I don't. I also need ax, ay, and az, which would introduce another variable, and I don't have enough equations. That's why I have to use moments. So, part 3, sum of the moments. Okay, and it's critical that I pick a good spot here. And I spoke with some students yesterday that were dealing with the 250 Newton pulling down force, and there's 2 pins and an extra pin at D. And everyone had some pretty good solid reasoning on why they picked that point. And so we're going to retain some of that thought process here, and we're going to say that we're going to choose it about point A, because if we choose the moments about point A, AX, AY, and AZ do not participate in the calculation because their moment arm is 0. So it's important that I pick a spot that gets rid of the most amount of variables possible so that I can solve for the ones that I'm close to solving, like TDF and TDE. Because I could take a moment about TDE, and then I would get AX, AY, and AZ, but I'm not close to solving those yet. I don't really have any good information about them. So I'm going to put the moment about point A, because I have 3 unknowns there, and I would like to knock them out and utilize the information that I've worked a lot on. So I'm going to choose the sum of the moments about point A, and that's going to be the summation of R vectors cross F vectors. And so we'll start with the first vector here, which is going to be the weight. I'm going to start in the far left. And so for the weight of the crate, I'm going to use the principle of transmissibility to move it down into the x-axis. So I'll essentially be moving it right there. Okay. Someone asked me yesterday, well, why don't I just take the x and y component of the weight applied to where it is applied? If I do that, I have an x moment arm and I have a y moment arm, but we all know what y cross y is. And so to skip that part, I'm going to say I'll just move it down to this point here. And that is going to be at a distance of 1.8 plus 0.84 plus 0.96, 3.6 meters. I'm going to cover this work. This would be fine right here. .6 meters. Okay, now, what direction is it in? The x-hat direction. From A, relative to the point of force application, the number is negative. It is going against the x-axis. So from A to the point of force application would be negative. So negative 3.6 meters x-hat is the moment arm or the weight of the crate. Okay, so that's the first R, and we're going to cross that with weight of the crate. And so weight of the crate is 3,000 newtons. It is acting in the Y direction. And since it is opposing the positive direction we have set for Y, the weight of the crate is negative. And that is our first R cross F.
Is it also okay to just inspect that it will be a positive product because it will be forcing the moment in the positive direction?
You can, but then you have to think about what axis it will be rotating about. And for these three-dimensional problems, it's much easier just to do the standard cross product where you have the negatives and the hats when you carry out the calculation. Because you're right, this will produce about the z moment of the z-axis. If I put my thumb out in the direction that it's coming towards me and I curl my fingers, Tori's right. The crate will produce a positive moment about the z-axis. But this problem's about to get messy, and so if I didn't include the negatives and the hats, I'm gonna get in trouble. So let's continue on with the next portion. And I'm gonna take gravity. Weight of G. What do I do in my notes? Yeah, let's do weight of gravity. Because we know weight of the crate and we know weight of gravity, which means these are just going to come out to numbers. I don't have to deal with variables yet. Let's do that. So the weight of gravity is 1.8 meters. And that'll be in the x-hat direction. And again, from A to the point G, yeah, I guess I need to draw it there too. Okay, so that is a distance of negative 1.8 meters from A, the place we're taking the moment about, to the place where the force is being applied. And we're going to cross that with negative weight of G. So negative 1,000 newtons y hat. And it'll be negative y hat for the same reason that the weight of the crate was, because it's acting downward against y, so negative. And that is our second R cross F. Okay, let's move on to one of the tensions. So we have taken care of, this is going to be really tough to see, but I don't want to get in the way of the drawing. We've taken care of weight of C. We've taken care of weight of G. And now I'm going to take care of weight, or the tension BH. Okay, and so the tension BH, moment arm, is going to be in the x hat direction, negative 3.6 meters, because it's at the same point that the weight of the crate is. I'm going to reuse that, negative 3.6 meters x hat. And then we're also going to have to add the y component, because if we use the principle of transmissibility, it only acts on its line of action. So I can either use it at B or at H. B is more conducive to what I've been working on, so I'm going to use it there. And so its height is going to be at a distance of 6.75 meters above. 6.75 meters. Y hat. So we're going against X, 3.6 meters, and we're going with Y, 6.75. And that concludes the moment arm for TBH. And so we're going to cross that with what we found down here as the tension in its Cartesian coordinate plane. So 2400 newtons X hat plus a negative 1800 newtons Y hat. And that is our third cross product. Okay, so these are all constants. These three will be constants. Now let's get into the variables. And the only ones we have left are TDF and TDE. So let's start with TDE. The moment arm for TDE relative to A is going to be 1.8 plus 0.84, 2.64 meters x hat direction, and from A relative to point D in the x hat direction is going to be negative. And add to that the y component, which is 4.95 meters. Y hat from A relative to D, that's positive value, so we're good there. And a good time to note that C, B, D, G, and H are all planar, and so they don't contain a Z hat component. So this is all I need to describe the moment arm from A to D, and we're going to cross it with these three components. Okay. Can I run Doom on my calculator? I cannot. What's good, Animal? Oh, Animals. Thank you for subscribing, sir. Appreciate that. Okay, so are we happy with the fourth cross product that we just populated here?
Just a quick question. Where did you get the Negative
2.64, the first
3.6
one?
meters on the one above.
3.6?
Yeah,
Okay.
I lost you on the diagram.
That's okay. This diagram has a bunch of terrible numbers here. And so from point A, I'm going to come up here and put 1.8 plus 0.84 plus 0.96. And so these three values, make sure I didn't mess that up. 1.8 plus 0.84 plus 0.96. Yeah, it's 3.6.
Ah, okay.
Yeah.
So
And
that's from A to B, correct? Yeah.
from A to B. And so I cheated because the weight of the crate has the same moment arm in the X direction. That's why I just copied it down.
Okay. Gotcha.
20 minutes of class left. Can I finish it? I didn't finish it in time yesterday, so hopefully I'll finish it today. Okay, and the last one will be TDF. And TDF acts at the same point in the moment arm, so I can copy that moment arm down directly. .95 meters. Y-hat direction. Cross that with. It'll be the same as the one above, except for the last component will be negative. Dang. .734. Negative 0.289. Z-hat. Okay. That's done. And this all equals 0. Okay, and now I'm going to sanity check. Where I have 1, 2, 3 knowns. Okay, and 2 unknowns. That one and that one. Okay, and AX, AY, and AZ don't participate. So I know that I've covered all of my cross products. TD. That's okay. The last bracketed statement is for TDE. No, the last bracketed statement is for TDF. So the first cross product is for the weight of the crate. The second one is for the weight of the boom. The third one is for the tension in BH. The fourth one is tension delta echo. And the last one is tension in delta foxtrot. Okay. Let's carry out the cross product. Okay, so when I'm going to carry out the cross products, let's draw that little diagram. X, Y, and Z. So if I go counterclockwise, it's positive, and if I go clockwise, it'll pop out a negative. So let's do negative 3.6 times negative 3,000. Okay, X cross Y is the right way, so this can remain positive. Z hat. Next one, negative 1.8 times negative 1,000. X cross Y. So this is also remain positive. Z hat direction. Okay. Third cross product. X cross X doesn't give us anything, so X cross Y. So negative 3.6 times negative 1,800. $6,480. And we did X cross Y, which pops out a Z hat. And since we did X cross Y, it remains positive. Okay, and now we're going to move on to 6.75 times 2,400 newtons. $1,600 Z hat. And this one was a Y cross an X. Y cross an X pops out a negative. So this will be negative. And so 1, 2, 3 of them done. Now let's get into the weeds with the two equations with variables. Yeah, it's Z hat. Okay. So moving on to the fourth bracketed statement. Negative 2.64 times. We don't get anything with X hat, so we'll move on to negative 0.734. $1.937 TDE. And we did X cross Y, which will retain a Z. And since I did X cross Y, no negatives pop out, and this will be fine. Okay, and now we're going to do negative 2.64 times the last term, which is 0.289. And that results in a negative 0.762 TDE Z hat. And since I did X cross Z results in a negative popping out, so I'm going to do this. And this is why I like to write plus the negative quantity, because if my cross product ever pops out with a negative like this, I can make that a positive. And so this shows me in my work that I took into consideration the negative and then I made it positive, because no one ever does plus open quantity plus the value. It doesn't really happen. So seeing this mathematical tendency shows me that I did the cross product.
If you did X cross Z, why did you end up with a Z hat?
Oh, dang. Because I've been on a Z hat roll. That's why. Thank you. It should be Y hat. I was ahead of myself there. I wanted to talk about the negative and making it positive. Messed up the cross product. Okay. So now we've done X cross Y and X cross Z. Now let's move on to the Y component of this fourth bracketed statement. So it's going to be 4.95 times 0.614 3.03 4.9 TDE. And I did y cross x, which will give us z hat. And y cross x is negative, so put a negative in here. Add that. Y cross y gives us nothing, so we're going to do y cross z. 4.95 times 0.289. .43 TDE. And that was y cross z, which gives us an x hat. And y cross z is in the positive direction, so that can remain positive. And now we're done with the fourth one. Last cross product to take into consideration. Negative 2.64 times x cross x gives us nothing. X cross y, negative 0.734. .93 T D Foxtrot. Okay, and that was x cross y, which will give us a z hat component. And x cross y remains the same direction, so that can stay positive. Next term, x cross z, negative 2.64 times negative 2.89, 0.289. .762 TDF, and that was x cross z, which pops out a y hat, and x cross z also pops out a negative. Okay, so that takes care of the first term. Now we're going to move on to 4.95 times 0.614. TDF, and that was y cross x, which gives us a z hat, and y cross x gives us a negative as well. Okay, and now we have 4.95 times y hat will give us nothing, and so we go negative 0.289. Negative 1.43 TDF. And that was y cross z. Y cross z will give us an x. And since it's traveling in the positive direction, that will remain negative. And this will all equal 0. That's got to be Tori's correction. Wilbur, did I miss that? Does this pulley system exist IRL? Yeah. Perfect. Thank you. Yeah, Wilbur, if you want, just interrupt me again, like Tori did. Just speak up and say, "Hey, you messed this up." Okay. Take a break. Shake it out. Cross product's done. Now the next tool that I can use is going to be splitting up the equations in x, y, and z. I might need more room here. Okay. So let's do for Newton's second law x equations. Oh, and I did this yesterday. I kind of liked it. So for the x equations, 1, 2. So let's do TDE first. 1.43 TDE minus 1.43 TDF equal to 0. So by inspection, this should be TDE equal to TDF. Right, so we just move the 1.94 or 1.43 to the other side, divide both by 1.43, and so you're left with TDE equal to TDE equal to TDF. Makes sense since we are equivalent or symmetrical about the XY plane. So I like that. Y equation. So same 0.762 TDE minus 0.762 TDF equals 0. And it looks like we come up with the same conclusion. So we know that X and Y plane, it's symmetrical. So we're good there. And so now the meat and potatoes part, the Z equation. Z. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's do the TDEs first. 1.937. .762. Or was I 1.97? I'm lost here. 1.97. Where'd I get this number from? No, that's not right. Copied it down incorrectly. Okay, let's start this again. Constant, TDE. Okay. Negative 3.039 TDE. TDFs comes next. 1.93. Okay. So that takes care of the variables. And I'm going to add to it the constants. So 10,800 plus 1,800 plus 6,480 plus negative 16,200. 2,880. And that should be newtons. Yes, newtons. All right. Let's move the 2,888 newtons to the other side, and we'll also combine these so we have a single number times TDE. So 1.937 minus 3.039 equals negative 1.1 TDE. And we'll have the same number here. But in TDF. And that will all equal, this number is positive. We're going to move it to the right side and it'll be negative. Okay. And so we have two variables, one equation, but since we know that TDE is equal to TDF, we can make the substitution. And so we will have, dropping the negatives off of everything, 2.2 TDF equal to 2,800 newtons. And so TDF will equal 1,309. And we'll also make that equal to TDE. 1 minute over. Okay. So, did we answer the question? The tension in the cables DE and DF. We found that to be 1,309 newtons. And part B says the reaction at A. I don't have enough time or space for this, so I'm going to give you a quick rundown on how to kick this from the driveway. Okay. So, if we have TDE, TDF, 1300 newtons, then these also become numerical values, just like TBH did right in the beginning. And so the next step here is going to be applying for 5 Newton's second law again. Some of the forces in the X, some of the forces in the Y, some of the forces in the Z, and this is where it's going to be AX, AY, AZ, oops, plus. And you'll be adding the components for these. So I kept you guys three minutes over. Thank you so much. Class is over. More than welcome to head out. I'm going to stop the Twitch recording now. Bye-bye, Twitch. Thanks for stopping by.